Welcome to the 2019 FRQs for numbers 1, 2, and 3. So if you're looking for 4, 5, and 6, that is a different video. When you're doing FRQs, questions numbers 1 and 2 are always going to require a graphing calculator. So if you know what question number you're looking at, you can know whether or not you're going to be using a calculator. Versus 4, 5, and 6. Or 3, 4, 5, and 6 will never use a calculator, or at least I guess I shouldn't say never, typically, from what we've seen in the past. So let's take a look at number 1. Fish enter a lake at a rate modeled by this function E. And so E is the rate coming into the lake. Fish leave the lake at another rate modeled by L. This is the rate out. So this is a problem that has both a rate in and a rate out. Both E and L are measured in fish per hour, and T is measured in hours since midnight, starting when T is equal to 0. Part A, how many fish enter the lake over a 5-hour period? We should be careful here because this is only asking for fish that enter and over a specific period of time. Well, this is asking for the number of fish as well. So we have rates. We want to undo the rate. And this is only how many fish enter. So I'm not going to be using the rate out at all. But this will be the definite integral from the time from 0 to 5 of E of t dt. I'm going to move to the calculator really quickly. And what I recommend is that as you start these FRQs, is go ahead and just define them. You have E, you have L, and I would just define them at the start of the problem and make your life a little bit easier. But this is the definite integral from 0 to 5 of E of t dt. Now let's see here. Let me change this. So this is 153.457. Now the direction specifically said 153.457, rounded to the nearest whole number. When they tell you to round to the nearest whole number, you should use the 0.5 rounding rule because 0.4 is less than 0.5, we will round down. Don't overthink this. We are just using the 0.5 rounding rule when we are told to round to a whole number. Part B, what is the average number of fish that leave the lake? So now we're talking about leaving the lake. And we're talking about average number. This is our average value formula. And again, we're using that same time period. Remember, average value formula is 1 over b minus a for your definite integral. And this one's going from 0 to 5. And this is of L of t dt. So I'm going to be calculating 1/5 of the definite integral from 0 to 5 of L. And since I've already taken the time to enter in both L and E, it's pretty straightforward from here. So 1/5 times the definite integral from 0 to 5 of L of t dt. And I get 6.059. 6.059. Now this one did not tell me to round, so I should not. This is all of the work I need to show for these two problems. All right, so when it's calculator active, you might have at times less work. You should still have something so they can tell what you're doing. Let's take a look at part C. At what time is the greatest number of fish in the lake? Justify your answer. This is actually a pretty challenging portion here of this problem. First of all, when you see the greatest number, you do want to understand that this is an absolute max. And this absolute max is over a closed interval. So we're going to use the closed interval test to solve this problem. So when I'm talking about the closed interval test, you use it for absolute extrema. And the closed interval test is when you figure out where the critical values are, because that could give you a relative extrema. And you also figure out where the endpoints are, which is given for you. And you test all of them in some equation for whatever function you're measuring. We're talking about the number of fish in the lake. I'm going to let A of t equal the number of fish in the lake. So I'm going to look at the number of fish specifically as being the number of fish coming in, starting at time 0. Now, this is the E, remember, is the rate of fish coming in, but I'm going to think of this as the number of fish is what I really want. So I'm going to integrate this. And then minus, oops, I can actually keep this in one integral because it'll be the same time interval, minus the number of fish that are leaving. And that also needs to be integrated. So I'll put that dt at the end. That's the number of fish. This is my function. If I want to find the greatest number of fish, I want to find out where the critical values are. So I do want to take the derivative of this expression, this equation. So a prime of t would equal, well, if I take the derivative of this right side by the second fundamental theorem of calculus, the derivative of an integral, when the lower number here is a constant, those will cancel out, and we will be replacing the top with whatever. I guess I could have changed that variable. Maybe I would have made this x. I don't know. No one's going to mark you down for that, but usually you have a different variable there. I'm going to plug t in instead. So this would be e of t minus L of t. And I want to set that equal to 0. So really what I'm looking for is where e of t and L of t are equal to each other. And that's going to be very, very helpful. Now, I can find this a couple different ways, but I would need to use my calculator regardless of the number of ways I do this. So I'm going to go ahead and take a moment to move to the calculator, and I'm going to use the solve function. Remember, on the solve function, you actually want to type out solve, and then pardon me, parentheses. I'm going to do e of t minus L of t equals 0. Now, certainly you could solve. You could move L of t over, but then you have to do comma t. And keep in mind, we're only looking for answers in the interval from 0 to 8. So I'm going to see that there's a couple different answers here, but many of these are not actually in my interval. So if I kind of scroll through these, this automatically will go in order from least to greatest. The only one that's in the interval from 0 to 8 is the 6.20356. Now, if your calculator didn't show that many decimal places, you should change your calculator settings. I have mine on fixed 5, and it's what I highly recommend. I'd recommend you just keep it on fixed 5 all of the time. So what I've got now is I now know what t is. These are equal to each other when t is equal to 6.20356. That doesn't automatically make this the time where we have the greatest number of fish in the lake, because that could happen at that t value or at one of the endpoints. What I need to do, though, is I now need to use that t value as well as check the endpoints, and I need to evaluate for a of t. Remember, a of t is the definite integral from 0 to t of e of t minus L of t dt. So if I plug in a 0 for this, a of 0 would be the definite integral from 0 to 0 of this expression, which we have a property of integrals that says if we start and end at the same value, that equals 0. If I want to do a of 8, this would be the definite integral from 0 to 8 of e of t minus L of t. And I'm going to use the calculator to evaluate that. So move back down here. So this would be the definite integral from 0 to 8 of e of t minus L of t dt. And I get approximately 80.91998. Now, be careful here. You do want to make sure that you write this down accurately to at least 3 decimal places, because if you don't, you will not get your justification points. Now, I often take it out a little bit further. That's totally up to you. I'm now going to do this at that 6.203564. A word of caution here. Do not, or 56, do not round this to 3 decimal places now and then plug it in. Keep that out to 5 decimal places until your final answer here. So I'm going to actually keep this and to 5 decimal places when I input this time, which was 6.20356. And again, I'm doing of E of t minus L of t. Oops, maybe, if I can do it right. dt. And I get 135.01492. This would be from 0 to 6.20356 of E of t minus L of t is approximately 135.041 or 01492. Since we're looking for the time where we have the greatest number of fish, and since this right-hand side tells us the number of fish, we have the most number of fish at that critical value. And so our final answer would be at t equals 6.20. You can round here if you want or truncate, and this would be hours. Now, a couple words of caution here when you guys are writing these down. What the readers are going to look for, they are definitely going to look for this. Now, you could write this alternatively, E of t is equal to L of t, because that would also be true if you just manipulate that equation a little bit. But that is something that they will be looking for that actually gets you a point. This part's worth 3 points, so there's 1 point right here. You get another point from choosing the correct answer. And then the last point's a very hard point to earn, which is all of this justification. And that justification, a really good way to earn that, honestly, is this. Those definite integrals are things that'll get you this point, as well as the output answer. But that last point is a hard point to earn. And so this is where students move from like a 4 to a 5, for example. All right, let's take a look at the last one. Part D. Is the rate of change, okay, that's language for a derivative, in the number of fish increasing or decreasing at 5 a.m.? Well, rate of change of the number of fish. Remember how earlier we said the amount of fish, or the number of fish, is right here? The rate of change of the number of fish we found earlier. The rate of change is E of t minus L of t. Now, though, we start using the word, is it increasing or decreasing? And those are also words to talk about derivatives. We need to take another derivative. So we are actually in this problem talking about a second derivative, because rate of change is language for a derivative, and increasing or decreasing is additional language for a derivative. So actually right here, oh crap. I want to take, sorry, I had a little issue there. I have to take the second derivative here, is really what this problem is asking me to do. So I'm really looking at what's happening with E prime minus L prime. And specifically, I want to look at that at 5. So I'm going to, in my calculator, go ahead and figure out what E prime of 5 minus L prime of 5 would be. So remember, I do have E prime minus L prime. I have E prime and L prime defined in here, but it might be helpful for me to maybe come up with some other rate. I'll call it R of t, that I'm just going to do as E prime, or E of t minus L of t. Okay, so that's what R would be, the original rate. I want to show if the rate's increasing or decreasing, so I'm going to take the derivative of R. I'm going to want this derivative to be evaluated at a point, so I'm going to go to Menu, Calculus, which is option 4, and Derivative at a point. I'm using t as my variable, and I want this to be evaluated specifically at 5. And I'm going to take a derivative of R of t. and I get negative 10.722. Now, this is going to be part of a final answer. I'm not going to have to use this again, so I can go ahead and round that if I'd like. This is about negative 10.7228. The most important thing about this is that I'm recognizing that this is negative, and this right here is pretty powerful. You do want to get that value, but you want to notice that it's negative. And because this is negative, our final answer here is that this rate is decreasing. But you do need either this inequality or to say that it is negative for that value. All right. FRQ number 2. This one's a particle motion problem, and it's also calculator active. So the velocity of a particle P moving along the x-axis is given by the differentiable function v sub p, where v sub p of t is measured in meters per hour, t is measured in hours. Selected values of that velocity of p are shown in the table, and we know the particle p is at the origin at time 0. Part A, justify why there must be at least one time on the closed interval from 0.3 to 2.8, right here to here, at which v prime of t, which is acceleration of p, equals 0 meters per hour, or meters per hour squared, if you'd rather. When you start talking about these at least one time, you might be thinking, at least one time? Those are probably going to be one of your theorems. MVT, IVT, EVT, those are ones you should be thinking about with this problem. And remember, there's also a special instance of the MVT with rolls that we could look at. In fact, that could be useful right here. So in this particular problem, since we're only looking from 0.3 to 2.8, make sure you are only looking at those values for this part of the problem. And we want the rate of change of V to be equal to 0. So when we're talking about rates of change and you're talking about the theorems, you might really want to be considering the MVT or the Rolle's theorem, which is a special condition of the NVT. The scoring guideline for this uses MVT, which is great because there's often more than one way to do this. I'm going to go ahead and use Rolle's theorem on this one. So Rolle's theorem does have some conditions, and we have to mention them. So one of the conditions is that we have to make sure that the function whose derivative we're talking about is both differentiable and continuous. We were told that this is differentiable. We have to mention it's also continuous. We also, if we're going to use Rolle's, should mention that V sub p of 0.3 is equal to 55, and that is equal to V sub p of 2.8. We want to show that they have the same output here. And so then we could say by Rolle's theorem, V sub p prime of t must equal 0 at least once in that closed interval from 0.3 to 2.8. In, over, could say a couple different ways. So basically what I did here is I just restated what Rolle's theorem says. So I identified it as being a match, and then I restated it. Now, another way to do this is to use the MVT, and that's actually the way that it was written on the scoring guideline. If you're using the MVT, you do need to actually use the slope formula. You could start off with this in kind of using functional notation, or you could actually just do 55 minus 55 over 2.8 minus 0.3 and show that that equals 0. And then you could say by the MVT, and again, since V sub p of t is differentiable and thus continuous, then V sub p prime of t must equal 0 at least once on that interval, 0.3 to 2.8. And so You could really use either one of these, but notice both of them really do precisely kind of restate out what the theorem says. And so that's something that you should be doing as well. All right, part B. Use a trapezoidal sum with 3 subintervals, and then they're going to tell you where we're starting and ending each of these trapezoids. We're going to go from 0 to 0.3, from 0.3 to 1.7, and from 1.7 to 2.8. So you might notice we are not even using this last column here for the trapezoid. So be careful, you may not use everything on the table. And we want to use this to approximate the definite integral from 0 to 2.8 of v sub prime of t. All right, so I'm going to write this out. A trapezoid is 1/2 times the height, which in this case would be the difference between the t values. This is the width because these are on their side. And then we want to add up both of the heights for that first trapezoid. I'm going to repeat this for the next one. This time, the width here is going to be the change again in the t values. This will be 1.4. I don't know if you can read that. And then times the sum of the heights. I want you to notice I put plus -29 instead of -29. It's probably not that big of a deal, but I do think it's a good idea. We want them to know that we know the formula for a trapezoid. And then 1/2 times 1.1 for that change in the t values, and then -29 plus 55. Now, on the AP exam, you could just leave your answer like this. Rather than inputting it into the calculator, and you could, I would just leave it just like that. I wouldn't input it unless I absolutely felt like I needed to. You also might notice that I wrote it slightly different than the scoring guideline. On the scoring guideline, they took these 1/2 and factored them out. Totally okay, you can do that. This part of the problem is only worth 1 point. And that 1 point, you either get it or you don't. So every once in a while they grade it kind of differently, but that's just kind of, this one's only 1 point long. Part C, a second particle Q also moves along the x-axis. Here's the formula for its velocity. Find the time interval during which the velocity of Q is at least 60 meters per hour. That's the first part of it. We also want to find the distance traveled by particle Q during the interval that we're looking at when the velocity is at least 60 meters per hour. So I'm trying to see where v sub q of t, the velocity, is at least, which would be greater than or equal to 60 meters per hour. So I'm going to do this graphically. I'm going to go ahead and graph the velocity function here. And then I'm going to use this velocity function to see where I'm above a height of 60. Hang on just a second. Let me pause this. Sorry about that. All right, so I want to look, I'm going to graph this and figure out where I can be, where v is higher than 60 or equal to. So I had been previously on this scratch pad, and I defined the velocity of q. I just called it q of t. Okay, this is the velocity for q. So if I toggle over to the graph portion, I want to graph this. Now I'm looking at this window. This is not a great fit for the problem because you might remember that the table for this went from 0 to 4. So I really I'm only limiting this to 0 to 4. And also I need my height to go all the way up to 60. So that's not really what my window is here. I'm going to adjust this window really quickly by doing menu, option 4 and option 1. And so I'm going to change the x coordinates from 0 to 4. And then for my y coordinates, I don't know. I don't really care what the min is, but I want this to be at least 60. I'll go 70. There's nothing graphed yet. All right, I'm going to go to tab and I'll enter in. You might remember I called it Q of t. Now, when you're graphing, you can't call it t anymore for the input. Graphing, you have to use x for the input. So there's what the velocity of Q looks like when graphed. Go back to tab again. Maybe not. Did something funny. Okay, and I'm going to enter in 60 for the height. And I can see that I'm above 60 from here to here. The question is, where are those values? I really do need to know where those values are. So I'm going to go ahead and go Menu, Analyze Graph, and I'm looking for the point of intersection. The first point of intersection would be from here to here. I'm just going to kind of pull that out of the way. You can see that 1.866181. And then there's another one over here. My labels are a little bit in the way. So I'll do Menu, Analyze Graph. Trace will not be accurate enough. Option 4, which is intersection. And I'll go to the left and right of this one. And if I kind of grab this and move it out of the way, this is 3.51917. Now, I do need to be writing some things down here about this. So I should be mentioning that V sub Q of T, I'm looking for where it's greater than or equal to 60. And this is on the intervals from 1.866, I'm going to carry this out a couple decimal places, to 3.519174. And what they want me to do is they want me to find the distance the particle's traveling on that interval. So total distance is implied here. So I will be finding the distance by doing the definite integral from 1.866181 to 519.174, and this will be the absolute velocity or absolute value of that velocity of q over time t dt. And then we would put this into the calculator from here, and we would get around 106.109 meters. Word problems, you should put those labels in there for the units. Sometimes they will specifically say to use units. Make sure you definitely do when they ask for them. So on this part of the problem, you might notice that I did not round these to 3 decimal places. That's because I had to use them again to find the total distance traveled. On the point values for this, if you are able to find out the interval, you get a point for those 2 t values. And then the definite integral that you write here, this whole definite integral being correctly written, is another point. And then getting the right answer on the calculator is the last point. All right, part D. At time 0, point Q is at position -90. Using the result from part B, oh darn, I guess I am going to need to put that in the calculator. That ends up being 40.75. I'd probably only put that in if I had to, into the calculator. And the function V sub Q from part C, approximate the distance between particle P and particle Q at time of 2.8. So we want to figure out where the particles are at, and these are both moving along the x-axis. So I want to find their position, is another way to say this. So I want to find the position specifically at time 2.8. Well, the position of particle P at 2.8 could be found by undoing the velocity of this function. And remember, it's starting at time 0. So this could be, I'm basically using the accumulation function. You might remember this one. F of B is equal to F of A plus the definite integral from A to B of F prime of X dx. Well, I'm going to say X sub P is kind of like our function F. So X at 2.8 would equal X sub P at 0, which you don't technically have to write because it is a 0, but it might help you understand it better, plus the definite integral from 0 to 2.8 of the velocity of function P, which we call V sub prime of T. V sub prime of T. All right, so then that will help me figure out where the position of particle P is at. I could then put that in the calculator. I'll get around 40.75. All right, I also want to figure out what is the position of particle Q. Particle Q's position I'm just going to name this as position of P, and this is the position of Q. This will help the reader know what I'm talking about. Would equal the position of particle Q at time 0 plus the definite integral from 0 to 2.8 of V sub Q of T dt. Oh, I left out my differential there. There we go. Which this one, the position of Q, V sub Q at 0, right here, they did tell us, let's see. Oh, right here. It was somewhere that we're starting out. Q is starting out at negative 90. So this would be negative 90 plus that definite integral. And that ends up being, which I think, yeah, we could use the calculator for that. And then we end up getting 45.937653. So if we want to find out how far apart they are, we should subtract them. So their distance, if I subtract them, 45.937653 minus 40.75. And so these are around 5.188 meters apart. As you will see, calculator active questions are no joke. And so they're ones you're going to want to practice, and you'll get better at them with some practice. All right, our last one is FRQ number 3. So this one we are not allowed to use a calculator. This one says we have a continuous function f defined on the closed interval from -6 to 5, as shown here. And we've got a portion of the graph. We're only here. Notice our graph only goes from -2 to 5, but it's defined all the way to -6. This graph is consisting of 2 line segments and a quarter of a circle. And the quarter of this circle is centered at 5, 3. This is the center of this quarter circle. It is known that the point 3, 3 minus the square root of 5 is on the graph of f. In other words, that's the ordered pair right here. All right, so for part A, if the definite integral from -6 to 5 of f of x dx is equal to 7, then find the definite integral from -6 to -2 f of x dx and show the work that leads to your answer. I often like to look and see which of these has a larger interval, and this one does. So we can take this integral from -6 to 5 of f of x dx, and we could split this up into 2 integrals from -6, this lower one should match, to -2, as stated in the problem, plus the definite integral from picking up where we left off, -2, all the way to this upper interval of 5. So we could split this up. We know that this one is 7, and this is what I'm trying to find, the definite integral from -2 to 6. And I can't find that by looking at the graph. Okay, you can call this whatever you want. I don't know. You could replace this with a variable if you wanted. But this part from -2 to 5, I can actually find this by using area models on my graph. And so that's actually what I'm going to be looking at. So I'm going to go ahead and calculate some areas. So from -2 all the way up to 6, this would be a triangle that's a 1/2 of 1 by 1. And then I have this negative triangle right here. Okay, it is going to have an area that's negative. So this is -1/2 of 3/2 for the base and 1 for the height. And then this next portion, remember I'm going all the way up to an area of 5. I'm going to stop right here at that quarter circle. This would be another triangle that's got a positive area. So plus 1/2 of this base is 3/2. And then the height here is 3. And then this part's interesting. I want to find this. This is the space between this quarter circle and the x-axis. So what you can do is you can think of this as like a rectangle. So if I've got a rectangle here, and this rectangle is a 3 by 3 rectangle, that's too much area. And I'm going to remove from that rectangle this quarter circle, which would be 1/2 of a circle with an area of 9 pi. Now this looks pretty different than the scoring guideline. I'd like you to notice the scoring guideline has everything kind of already simplified out versus we've got everything still really worked out here. If you do all of the simplification, you would end up with, let's see, this would be 1/2 minus 3/4 plus 9/4 plus 9 minus 9 pi over 4. Now what I'd like to do is isolate the definite integral, so I'm going to be moving things around here will be the ultimate goal. Let's see if I did my computation correctly. Let's see, 9/4 minus 3/4 would be 6/4. And then I have this 1/2, which is 2/4 plus 6/4 for this portion, which would become 8/4, which is 2. And then plus the 9 from the rectangle that was too big, and minus the 9 pi over 4. So if I move things around a little bit, I'm going to subtract 11 off from both sides. I'll have, and I'll add the 9 pi over 4. I'll have that this definite integral is equal to positive 9 pi over 4 minus 4. And I left off my dx, which is actually quite the problem, because if I actually did leave off the dx here, they would assume my definite integral went all the way to the end of the expression. So I should be very, very careful here to make sure to include that dx. All right, that's part A. By the way, on part A, this is worth a fair number of points. This is worth 3 points. You can get the first point just from setting up the property. That's one of the points. Another point comes from all of the area model over here, even if you have it on the wrong side of the equation for some reason, okay? So even if you screwed up on the properties from the beginning, but you need to calculate those areas, you could still get 1 point from that. And then the final answer is the third point. Part B, we want to evaluate the definite integral from 3 to 5 of 2 times f prime of x plus 4 dx. I think for me, I understand this better when I split this up a little bit into more than one integral. I'm going to take this first part and write it as its own integral, and I'm going to take the 2 out front. And then separately, I'm going to evaluate the definite integral of 4. Well, the integral of f prime, the integral and the derivative here, those are going to cancel out, which is pretty nice. And so this would be 2 times f, but f is being evaluated at 5 and at 3. The integral portion canceled out, but the fact that we are subtracting these is still true. Notice it's no longer an integral, canceled with the derivative. Well, the integral of 4 is 4x, and then we evaluate that at 5 and 3. Be careful, don't just put a 4 here. Well, if I look at the diagram, f of 5 is 3. So this is 2 times 3. Let's see. F of 5 is not 3. I fooled myself. Oops. F of 5 is 0. So 2 times 0 minus f of 3. Well, they gave us f of 3. This very obnoxious number here, which is, let's see, 3. I'm going to put this in parentheses, 3 minus root 5. Like that. And then we want to subtract off from that f of 3. And so f of 3, there's f of 3 right here. Oh, I already did that. Sorry. And then plus 4 times 5 minus 3. You don't have to actually evaluate this. You can leave it just like that. And then you would end up at the very end, if you wanted to continue to do all of your computation there, you could, but you don't have to. All right, part C, the function g is given by the definite integral from -2 to x of f of t dt, and we want to find the absolute maximum value. Well, absolute maximum, just like with absolute minimum, closed interval test is what you want to use. So you want to start off by finding out where the critical values are, and you also want to test the endpoints. So we are going to be looking at x values of -2 and 5, and I need to figure out also if there's where any critical values are. Well, critical values would be where the derivative is equal to 0. Well, if I take this equation and I take the derivative of both sides, I'd get g of x is equal to f of x. I use the second fundamental theorem right here. If I set that equal to 0, this is going to tell me where the critical values are. I'm going to look at the graph to see where f is equal to 0. F is equal to 0 actually a couple different times in this problem. At -1, at +1/2, and at 5. Now, I already had it at 5, but this would be all of my critical values at -1, +1/2, and 5. Those are going to need to be included as well. And I'd like you to notice I didn't have to write the 5 again. I already had it written down. Well, since g can be found by doing the definite integral from -2 to the x value, which in this case is -2 of f, that's what I will use to calculate this out. We have a property that says that would equal 0. And then if I did from the definite integral from -2 to 5 of f of t dt, I think we already did that earlier. As we were working on part A, we had to calculate the definite integral from -2 to 5, and it ended up being this part. I don't need to show that work again. That'd be 11 minus 9 pi over 4. I should, however, show the definite integral. And then the definite integral from -2 to -1 of f of t dt. From -2 to 1 is this triangle right here, which is 1/2 of 1 by 1, or 1/2. And then from -2 to +1/2 would be this triangle and this one. So that would be, of f of t dt would be 1/2 of 1 by 1 minus 1/2 of 1 by 3/2, which is -1/4. And we want to find the absolute max. So looking at this one, the absolute max here, we've got a 0, we have a negative, here's a positive 1/2. Remember 9 times pi, this is like 27-ish, divided by 4. 11 minus about 27 divided by 4 is maybe close to 8. This is like 3. This is our biggest value. So the max value, when they say value, they're talking about the y value or the output. And so the max value here is 11 minus 9 pi over 4. All right, the last part. We want to find the limit as x approaches 1 of 10 to the power of x minus 3 times f prime of x over f of x minus the arctangent or the inverse tangent of x. Well, your first method for finding limits is to go ahead and do the substitution. So I'm going to go ahead and substitute in a 1. So this would be 10 to the power of 1 minus 3 times f prime of 1 over f of 1 minus the inverse tangent of 1. This would be, you might notice I don't like to use arrow or equals, I'm using arrows. This would be 10 minus 3 times f prime of 1 is the slope at 1. So if we look at this one, if we look at rise over run, this is up to and over 1. So that was the slope of f at 1. F of 1 specifically is 1. And the inverse tangent of 1 is saying what's the angle that has a tangent of 1, which is pi over 4. And you could leave it just like that on the AP exam. And that is the end of our solutions for this section.